Okay, so I'm going to start reviewing for the final, and this is all we're going to do today and tomorrow. There's no quiz tomorrow. Um, so yeah, I put out a final review sheet, so have a look at that and ask me any questions, but I'm just going to go ahead and review some stuff that I think is pretty safe to review. This is like the early stuff that people may have forgotten. So this is all first order differential equations. There's no y double prime or y triple prime. And there was basically four types that we covered. Oh, maybe we covered a little bit. Maybe we covered like five types, but they aren't all going to be on the final. So if you remember, probably the first and the easiest is separable. If you solve it for y prime, that's going to be a function of x times a function of y. And of course, what you do is you separate the variables. So y prime is dy over dx. And then you move this over here to get dy over this. And you move the dx over to the right to get f of x dx. And the next thing you would do is integrate both sides, right? First order linear looks like this. Sometimes you have to do some algebra to get it to look like that. What you're going to notice about this form is there's a very limited way that y can appear. Specifically, you're not going to see y squared, you're not going to see e to the y, you're not going to see cosine of y. You're not going to see any function of y except for just y times maybe a function of x. So y kind of appears just as a plain y. There's never any y squareds or sine y's or anything like that in a first order linear. In other words, it's linear in y. So, and if you remember, what you do is you just multiply both sides by this thing that we call the integrating factor. It was rho, it's e to the antiderivative of p of x, where p of x is this thing. Yeah. Then there was homogeneous differential equations, which is where if you solve it for y prime, you can write it as a function of y over x. And in terms of the algebra, you often see like fractions with the same power of y over the same power of x, like y squared over x squared, or x cubed over y cubed. If you see stuff like that, that's kind of a giveaway that it's a homogeneous differential equation. And what you do is you substitute v is y over x, and then y would be v times x, so y prime is vx prime, which is this according to the product rule. And you now go to the differential equation, you make the substitution, and the new differential equation should be separable. Let me write that. And then there's exact differential equations. These are probably the hardest to recognize. I'm going to be nice to you, and I'm going to give you, well, not an explicit hint, but I'm telling you what the hint is now. If I write dx and dy in the statement of the differential equation, that's my hint to you that it's exact, right? Because I could do that on all of them, like wherever I write a y prime, I could write, dy over dx, and you may find yourself writing dy and dx when you're solving it, but I'm not going to write dy and dx unless it's exact. So that's my hint to you. Otherwise, exact differential equations can be hard to recognize. But once you have a hint that it's exact, what you should start looking for is what we call the potential function, which is this function f whose partial derivative with respect to x is this, and whose partial derivative with respect to y is that. And once you find an f, then you're basically done. You just set that equal to a constant, and that's the general solution to the differential equation. So yeah, I just wanted to review those real quick because you're going to have at the very least you're going to have one of each on the final, and they're going to be mixed up. You're not going to know what kind is what. You'll have to recognize them. Um, that can be one of the hard skills for this class is recognizing the different types when you don't know what they are. Um, so I have four differential equations here, and we're going to solve each one. But before we even solve each one, let's decide what's what. So maybe, yeah, maybe if I'm going to be most efficient, the easiest one, of course, is to recognize the exact one based on my hint. I only wrote dy and dx on one of these. So this should hopefully be exact. Then what? For these other ones, besides the exact one, often the best thing to do is to solve for y prime. So if I solve for y prime here, I'm going to get x squared plus 2y squared over 2xy. And, well, okay, so I can think about that. It's not particularly looking separable. Like if it was separable, then when I solve for y prime, it should be like a function of x times a function of y. And, you know, there's always the possibility that there's some algebra to do here, but I see addition, like a function of x plus a function of y over here. So I'm thinking it's probably not separable. It's also not linear, so I see y squareds and stuff like that going on, and so this is not going to be linear. It is homogeneous, though. Of course, maybe I'm kind of doing process of elimination, so we hope it's homogeneous. But if you think about it, it really is homogeneous. This is the same as x over 2y. Like I'm dividing each one by 2xy, and I can cancel some stuff. Plus y over x. So, right, I see these fractions, and it's always the same power of x over the same power of y, meaning if I see an x to the 1 on top, I see a y to the 1 on bottom, and vice versa. If I see y to the 1 on top, I see x to the 1 on bottom. So this is homogeneous. And we'll actually solve that later, but for now, let's just go through and declare what type each one is. So I got A, I got C, what about B? Again, maybe the best thing to do if I'm not looking at an exact one is to solve for y prime, but well, and maybe this is because I know the answer already. I'm not going to solve for y prime all the way. Let me just do one step. I'm going to divide by the x. And if I wanted to solve for y prime all the way, of course, I could just move this over, but that's easy stuff. So this, well, even if I moved this over, I don't think it would be separable, right? Because even if I moved this 2y over x over here, it wouldn't be a function of x times a function of y. It also wouldn't be homogeneous. Like I've got y to the 1 over x to the 1 here, but this x squared would be messing it up. This isn't x squared over y squared. It's just a plain x squared. So if I'm thinking homogeneous, I don't like that. However, it is linear, right? I've got y prime. This would be my p of x. This would be my q of x. So Yeah, and well, of course, it's tempting to just say the last type is the last type because a process of elimination. I said I was going to give you one of each, but let me say something smarter than that. Um, this one, again, I can do the same strategy. I can solve for y prime. And this is a function of x times a function of y. If I want to really, well, okay. This is 1 over x times, and yeah, well, I'm really writing too close to the edge here, so let me just make that clear what I meant. That is a function of x times a function of y, because I can just separate it like that. So this one is separable. All right, so we characterized each type. Now let's solve all of them. So part A, we said was homogeneous, and actually let me not even write it this way. Let me write, because we already said what this was. This is, so y prime is x over 2y plus y over x. And what do you do if it's homogeneous? You substitute v is y over x. So I'm going to say v is y over x, y prime, and I'm just going off of here. This is always the same. Y prime is x v prime plus v. So let me rewrite this differential equation. Y prime is x v prime plus v. This would be 1 over 2v, right? Because v is y over x, so x over y would be 1 over v. This is just v. Yeah. And what's supposed to happen is after making this substitution, the new differential equation should be separable. So, cancel the v's, and then I can write v prime. So actually, since we know it should be separable, let me write dv over dx. So x times dv over dx equals 1 over 2v. Let me separate the variables. So 2v dv equals dx over x. Integrate both sides. I get v squared equals natural log absolute value of x plus c. It's a constant. And then I just want to state my final answer in terms of the original variables. So just remember that v was y over x. So this is y squared over x squared equals natural log absolute value of x plus c. And I could solve this for y if I really want an explicit solution. As usual on the final, unless I state otherwise, which I almost never do, implicit solutions are just fine. So also we don't have an initial condition, so we can't solve for c. So we're done. Okay, let's do part B, which was this one. Okay, and remember, we already did this work when we were figuring out that this was a first order linear. So I'm going to go off of here. So y prime minus 2y over x equals x squared. And actually, instead of 2y over x, I wrote it this way because this is my p of x. So rho is e to the antiderivative of p of x So that's e to the negative 2 natural log absolute value of x. We don't bother writing plus c here. And we want to simplify this. So this negative 2 comes up. E and the natural log cancel. So this is 1 over absolute value of x squared. And because it's squared, the absolute value doesn't do anything. So it's just 1 over x squared. So that's rho. I'm going to multiply both sides by rho. And so what happens on the left, it is always the derivative of y times rho. On the right, you have to think I'm multiplying x squared by this. So I'm actually just going to get 1. Then I do the antiderivative of both sides. And now I do have a plus c. And then, I could leave it like this. Somehow, I feel like solving for y, though. But I would accept this as an answer as well. So yeah, that's most of these are easy. Like, you just have to be able to recognize what type they are. You do have to remember some basic like integration skills and stuff like that. But anyway, let's do part C. We decided that C was exact. So what do you do if it's exact? You start finding this function f. So just to be clear, its derivative with respect to x should be this. So what we can tell off of this is the following. If I do the antiderivative of this with respect to x, what am I going to get? The antiderivative of cosine would be sine. This is just a function of y. This would be constant with respect to x, and the antiderivative of a constant is just that constant times x. So it's just that constant times x. Plus something else. When we do an antiderivative, and we're doing an antiderivative with respect to x, usually you put plus a constant. This quote-unquote constant could be a function of y. It's only a constant with respect to x. It could still be a function of y. So this is what we know about our potential function so far. It has this form. It's sine of x plus x ln y plus possibly something else, but there's no x's in here anymore. What do we have still? We have to check this other thing. The partial derivative with respect to y is supposed to be this. And this will help us fill that in. Being a little bit redundant here. But let me rewrite this line. Now, we should already see some of this. Like, if I take the part that I already know and I did the derivative with respect to y, well, this part would go away. This part would turn into x over y, and I see that here, so I like that. What I don't see, I don't see anything here that if I took the derivative with respect to y, I would get this. So that's what's missing. What's missing here is a term whose derivative with respect to y is that. Of course, that term would just be e to the y. And that is the missing function of y. So now we're good. We can check that we're done. If you get confused and you're wondering if you're done, just look at the function that you have and do the partial derivative with respect to x and check that you get that. Do the partial derivative with respect to y and check that you get that. And we're all good. So the solution is just that this equals a constant. And again, there's no initial conditions on any of these, so we're not going to solve for C. Okay, so let's do the last one. If you remember on the last one, we said it was separable. We got it down to this point, y prime equals this. So actually, I got a little bit ahead of myself when I wrote this. Let me write, this is the same thing we had on that page. I'll go from there. But, right, what I'm doing is I'm separating the variables. So y prime is dy over dx, and then I'm moving the y's over here, and I'm moving the dx over here. So on the right, I'm going to have dx over x, and on the left, I have dy, and I have to divide by all of this. So I'm going to have the reciprocal. And yeah, that's where I was trying to start from, but I just wanted to justify that a bit better. So the variables are separated. What I do next is put an integral sign on both sides. And now, you just have to remember your integrating skills. This one is not arctangent. If this was 1 over 1 plus y squared, that would be arctangent. But this is y over 1 plus y squared. The way to integrate this is to do a little u substitution for the bottom. Du would be 2y dy. So this turns into basically 1/2 du over u. Yeah. And then this side's easy to integrate. So yeah, it looks like I'm basically done. Let me put my answer together here. On this side, I did the antiderivative. I got this. I should replace u with what it is, so I should have 1/2 natural log absolute value of 1 plus y squared. On this side, this is just natural log absolute value of x, and I should put a plus c somewhere. When I integrate both sides, I should put plus c. It doesn't really matter which side I put it on, but yeah. And I can simplify my answer. Of course, here I'm clearly doing the natural log of a positive number, so these absolute values aren't doing anything. But we don't have to simplify the answer. Once we get to this point, we can just call it good. Okay, so that's the 4 types, and this video is getting almost 25 minutes, so let me stop it and do something else.